Welcome to the Deep Dive, where we plunge into the most fascinating and often hidden corners of the world to bring you cutting-edge insights. Today, we're diving deep, literally, into a critical field that underpins some of humanity's most ambitious engineering feats: offshore geotechnical engineering. We're drawing our insights from a really definitive text in the field by Mark Randolph and Susan Gorvanek.
That's right. And it's fascinating, what's truly captivating here is how the challenges offshore, you've got the immense scale, the unique construction methods, and those complex installation techniques. Well, they haven't just adapted onshore practices.
Right.
They've actually driven the creation of a completely specialized discipline. It's really diverged significantly over the last, say, 30 years to meet these unique demands.
So our mission for this deep dive is to explore exactly what makes this world beneath the waves so uniquely challenging. How do engineers gather crucial, often elusive information from it? And then the ingenious solutions they develop to build safe and effectively. It really is a story of human ingenuity meeting nature's immense power.
It really is.
Okay, let's unpack this then. When we think about building offshore, it's not just about the water, is it? The ground beneath the ocean is an incredibly dynamic and often hidden frontier, full of surprises, I imagine.
Oh, absolutely. We often think of the seabed as static, but the Earth itself is an active, constantly moving planet.
Yeah.
I mean, think about the groundbreaking theory of continental drift. Alfred Wegener, the German meteorologist back in 1915, he vividly described continents drifting about like icebergs in the sea.
A powerful image.
It is. And this constant slow-motion geological movement profoundly shapes what we call the continental margins, those underwater slopes and plains leading away from land.
And those are key areas, right?
Exceptionally important, not just geologically, but because they hold nearly 75% of the world's marine sediments, despite covering only about 20% of the total ocean floor. So they're critical for energy resources, but also incredibly complex geologically.
That's a powerful reminder of how dynamic our planet is. Does this constant geological movement present unique, ongoing challenges for structures that need to last for decades? Or is it more about finding stable zones to begin with?
Well, it's both, actually. You absolutely have to identify stable zones first.
Okay.
But even then, the regional geological activity dictates the types of soils we encounter. And this brings us to another key difference. The actual soil engineers find offshore is often distinctly different from what you'd find on land. A whole different ballgame.
Right. So what are some of those unique characteristics? How does marine sediment differ from, say, the dirt in my backyard?
Well, marine sediments vary hugely in composition and thickness. They tend to be thickest closer to continents, where rivers dump vast amounts of material.
Makes sense.
And thinnest on newly formed mid-oceanic ridges. They primarily originate from two places. Land, we call that terrigenous deposits, often sand, silt, or clay carried by rivers, or from the remains of marine organisms, which are pelagic sediments like the shells and skeletons that slowly drift down.
Wow.
But a critical aspect for engineers is their in situ stress state, basically how compressed and settled they are in their natural environment.
How stressed they are, essentially.
Exactly. These sediments can be normally consolidated, meaning they've settled naturally over time under their own weight, or over-consolidated if they've been under higher pressures in the past, maybe from glaciers or something.
Right.
Or even, and this is where it gets really tricky, incompletely consolidated.
You can completely consolidate. Okay, what does that mean for an engineer trying to build something massive on it? That sounds precarious.
It means that excess pore pressures, essentially, water trapped within the soil that hasn't had time to escape, haven't dissipated.
Ah.
So imagine building on a saturated sponge that hasn't fully settled. It's a big problem. This is particularly common in rapidly deposited areas, like river deltas, or where runout from a submarine landslide has recently come to rest. These soils are highly susceptible to sudden settlement or even liquefaction under load.
Yeah.
It's not just a detail. It's a fundamental challenge that dictates everything about how we design foundations to prevent catastrophic failure.
Right.
Another unique type, carbonate soils, for instance. They're prone to particle crushing at relatively low stress levels, so they end up being much more compressible than, say, common quartz sands, which again significantly alters design considerations.
So we're talking about a moving planet and these incredibly varied, sometimes unstable sediments, and then there's the immense body of water itself constantly moving, interacting with the seabed. That's another layer of complexity, isn't it?
Indeed. A huge layer. We deal with complex patterns of currents, both horizontally and vertically, on a global scale. Surface currents are primarily wind-driven, sure. But in the deep ocean, the currents are driven by variations in density due to temperature and salinity, what's known as thermohaline circulation. People often call it the global conveyor belt.
The global conveyor belt, right.
It's this vast, slow-moving system. And here's a truly surprising fact. It's estimated that any given cubic meter of water can take around 1,000 years to complete its journey along this belt.
1,000 years, wow.
Think about the sheer volume and continuous motion. And then you have surface waves too, obviously. They're a critical factor. Their size and energy determined by wind speed, wind duration, and the fetch. That's the distance the wind blows in a single direction.
Okay.
These combined forces create a perpetually active and challenging environment, putting immense fatigue and extreme loads on any offshore structure.
So it really highlights for us just how many active dynamic elements engineers are contending with offshore. It's not just a static seabed.
Yeah.
You've got a moving planet, dynamic and unique sediments, and that immense circulating body of water. The scale and dynamism are just immense.
Exactly.
Which, of course, begs the next crucial question. How do engineers even begin to see what's down there, let alone gather enough reliable information to build safely? This must demand incredibly specialized techniques.
That's precisely the challenge. And yes, it demands incredibly specialized techniques. You can't just send someone down with a shovel.
Right.
You need a reliable model of seabed stratigraphy, essentially a map of the layers below the seafloor, and precise quantification of the engineering parameters for each layer.
Yeah.
It's absolutely essential. The process typically integrates